Okay, so let's quickly recap what we discussed last class in terms of MOSFETs. When you think of MOSFETs, what do they mean, right? So always remember you have two kinds of MOSFET, an NMOS and a PMOS. Symbol for the NMOS is with an arrow. So the arrow is always at the source end of the transistor. So this is the source, drain, and gate. PMOS is represented with an arrow in the opposite direction towards the gate, right? Or sometimes you can see an NMOS which look like this. So this is especially true in digital design, where the NMOS looks like that, and where the PMOS looks like with the bubbled input, right? And so if you think about the NMOS, right? Again, in all transistors, VGS controls IDS, right? So what you apply between the gate and source, the voltage you apply between the gate and source controls the resistance you see between the drain and source. So these are electrical switches, if you will. That's how we're going to use them in digital design, right? And so remember, in the case, and we talk about VT. Sometimes you see these terms VT and VTN and VTP or just VT. So VT is the threshold voltage of the NMOS. VTP is the threshold voltage of the PMOS. So NMOS works as when VGS is less than VTN, IDS is zero, right? So when VGS is less than VTN, my drain to source are disconnected. So it's an open circuit. Only when VGS is greater than VTN, my IDS is a finite value, right? So IDS is greater than zero, right? So we see two stages depending on the input voltage. If the input voltage is less than VTN, then my drain and source are disconnected. And my drain and source are connected only when my VGS is greater than VGH. In the PMOS, it works in the other direction that VGS has to be less than VTP for my IDS to be greater than zero, and my VGS has to be greater than VTP for my IDS to be zero. Again, remember here, VTP tends to be less than zero, VTN tends to be greater than zero, right? So for the PMOS to work, its gate voltage has to become more negative than the threshold voltage. For the NMOS to work, the gate voltage has to become more positive than its threshold voltage. Okay, just remember that. Okay, so this is all we need to understand how to design digital gates using MOSFETs, right? And then we looked at a simple NMOS inverter. So sometimes an NMOS inverter, which is, so remember, we are talking about multiple technologies. One is an NMOS technology. So in the NMOS technology, the only transistors you're allowed to use are NMOSFETs. And then we talk about the CMOS technology, which is your important technology, which is the workhorse today. And that includes both P and NMOS, right? So we all saw last class that if I had a circuit which looks like this, and if I pull the output from the drain of the circuit, then we saw that V out can be thought of as V in bar, right? So this is an inverter that has been implemented in NMOS logic, right? And so the other way, so we normally implement resistors. So we want to implement resistor as a transistor which is always on. So what we will do is we can implement a resistor which looks like this. Right. So if you look at this resistor, remember this is a drain, source, and gate, right? So VGS here is very high because this is VDD, right? So this transistor is always on, and from that you can get the relationship that Y is equal to A bar. So again, whenever you look at NMOS circuits, right, look at what is below the output, right? So what is below the output dictates what the output is going to be. So we also looked at two others. Suppose I want to do an NMOS on the NAND gate, right? So what does a NAND gate do? NAND gate definition is given by y is equal to a dot b whole under the bar. So y is going to be high for most of the times. Remember, NAND gate is a mostly high output gate, right? So NAND is going to be high for all outputs, whether AB is 0, AB is 1 0, or AB is 0 1, right? Y goes low only for one combination. And that combination is when A is equal to high and B is equal to high, right? So only for this combination does this gate go low at the output. So when you design this, right, we want, so again, think about an NMOS only circuit. This is your output Y, right? So you have one transistor here and you have another transistor here. Again, so for this Y to be pulled to ground, you need to have both transistor M1 and transistor M2 to be shorted, right? So which means both A and B. So when both A and B are high, only then will Y be connected to ground. For all other combinations, either one of the transistors is going to be open. So at that point, Y is going to be close to VDD, right? And so another way to implement that would have been so replace the resistor with an NMOS transistor. So this would be your NAND circuit. So Y is A, B under the bar. It's a NAND gate. So a NOR gate, however, on the other hand, is a mostly zero circuit, right? So NOR is going to be high only when A and B are both zero. For all other combinations, NOR is going to give you a zero output, right? So the way you design the NOR output is this way. You have two parallel paths. So again, this is your output Y, and you have two parallel paths for Y to discharge. Right? So Y can go to zero either when A is high or when B is high, right? So Y is equal to zero when A is high or B is high. And so this is nothing but your NOR gate. So Y is equal to A NOR B. So again, what you see here is if you look at the circuit below Y, right? If I look at the circuit below Y, if I want to implement an OR function, I need to have multiple paths for discharge. And if I want to implement a NAND function, I need to have series paths. Okay. So remember that whenever, so for example, suppose I wanted to implement a function like this. Let's say, so if I ask you, how would you implement this function in an NMOS only technology? Can you quickly think about it? Using the same logic we just did, think about how would you implement this in an NMOS only technology. We'll do it together, but you take a minute, figure out what it is, then I'll discuss the answer. So Abhin, for now, use the resistor. I'll talk about that later. Use a resistor right now and tell me how do you implement an A plus BC whole under the bar. Correct. So again, what do you want? So Y, you want Y to go to zero only when either A is high or both B and C are high, right? So if I look at the pull down circuit or the circuit which is connected below Y, if this is my Y, right? Above that I have a resistor. So Y can go to zero either through A, right? Or it can go to zero through a series connection of B and C. right? So if I think of the circuit, I can implement this again. Remember, this is easy to implement because the whole thing is under the inverter, right? So again, any NMOS logic or CMOS logic likes to have expressions written in this form as the complement form because it's easy to implement. So therefore, NAND and NOR become our universal gates because they're easy to implement in CMOS, right? And so if I want to implement this function, think about it again. Y will be pulled to zero either through this path or through this path, right? And this path will be enabled whenever A is high. And this path will be enabled when both B and C are high, right? So it is A plus BC, the whole thing under the bar is how you implement this circuit. Everybody with me? Any questions here?
So where is VDD?
So VDD would be connected through a resistor here to VDD. Right? This top part of the circuit remains the same. It's only the bottom part that's changing in an NMOS technology. Now we'll move to CMOS. In CMOS, we'll see both sides have to change. Any questions? Any other questions? Okay. If there are no other questions, now let's look at. So I gave you one question at the end of last class. I don't know how many of you got to thinking about it. That is CMOS technology. So why is CMOS technology used? CMOS technology is your low power technology. It has the lowest leakage among all the MOSFET technologies available, right? So low power technology. So hence CMOS is the most prevalent technology. Okay. So let's think about the circuit I gave you yesterday. Sorry. So M1 is the NMOS, right? And M2 is PMOS. Okay. So now let's think about how the circuit works. Okay. So now let's assume suppose A is high. So when A is high, right? What happens to the NMOS? VGS is high, right? So the M1 is shorted, right? What about M2? A is high, so GS is actually zero because A is high, so S is also connected to VDD, right? So VDD minus VDD is zero. So VGS is zero for this transistor, which is greater than VTP. Remember, VTP is negative. So what happens is M2 is open. So when A is high, M1 is shorted, M2 is open. So what do you get? You get zero, right? And when A is low, what happens in that case? So when I give a zero here, right? When I give a zero here, M1 is shut off. So M1 is open, right? And M2, if you think about M2, M2 applied a zero here, there's a VDD here. So VGS is minus VDD, which is much more negative than the VTP. So M2 turns on or M2 is shorted. So in that case, your Y becomes pulls up to 1. So what you see is when or Y is low. Let's not call 0, 1. Let's call low and high. Right. So what you see is when A is high. So if I draw the truth table, when A is high, Y is low. And when A is low, Y is high. Right. And so this is an inverter. Can take a minute to look at it carefully. If there are any questions, please ask. Okay. Now let's think about a slightly more complicated gate, which is the NAND gate in this technology. So everybody following the CMOS inverter? I'm hoping there are no questions. Again, if you have any questions after the class, please send me an email. So let's look at a CMOS um, NAND gate. Okay. So again, how do we think about it? So again, when you think about CMOS, one common feature is that always remember when you're designing CMOS gates, when designing CMOS gates, one input has to go to both N and P. So for example, if you see this A input has gone to the gate of both the PMOS transistor and the NMOS transistor. So whenever you design a CMOS, you'll see that all your inputs will not go to just one gate. If you think about the NMOS technology that we designed previously, every input just goes to one gate, right? Like in this case, A goes to this transistor, B goes to this transistor. Similarly here, A goes to one transistor, B goes to one transistor. So in the NMOS and only technology, every input goes to a single transistor, right? But now when you look at a CMOS technology, you see that a single input goes to one PMOS and one NMOS, right? So now let's think about a NAND gate, okay? So again, what do we know about the NAND gate is we want to implement y is equal to A, B whole under the bar. So from the NMOS technology, I know that if I want to pull the Y down, below Y, I should have two NMOS transistors in series, right? So if I think about it, if this is my if this is my node Y, right? I know that below that I should have two transistors in series, right? So one would be an input A, one would be an input B. So this part of the circuit will ensure that Y will go to 0 only when both A and B are high. Everybody following me? This was the same logic from the NMOS circuits, correct? Now let's look at the flip version, right? So in the flip version, what happens when when should Y go high? Y should go high when either A or B or both are 0, right? So Y should go high when either A or B or both of them are 0, right? That is the NAND gate. So which means that Y should charge up to 1 even if A is 0 or B is 0, right? So there should be two methods to charge up Y because I want to ensure that Y goes to 1 independent of whether A is 0 or B is 0, right? So what you see is that to charge up Y, therefore, I need to have an OR connection. So which means that when A is 0 or B is 0, one of these PMOS transistors are going to be turned on, which is going to pull this Y to 1. Everybody following? So what you see is that, and so basically you have, again, you have input A connected to this PMOS transistor, you have input A connected to this PMOS transistor and this NMOS transistor. You have input B connected to this PMOS transistor and this NMOS transistor. Again, how do we think about this circuit? Let's recall. Y is going to go to 0 only when both A and B are high. Remember, NMOS will be shorted only when a high voltage is applied at the gate. PMOS will be shorted only when a low voltage is applied at the gate. So that's another way to short to keep in mind, right? Whenever you want to short an NMOS transistor, you apply a high voltage at the gate. When you want to short a PMOS transistor, you apply a zero voltage on the gate or a low voltage on the gate, right? So what you see here is that Y will be pulled to 0 only when both A and B are high. For all other combinations, Y will not go to 0. Y will go to 1 only when will go to 1 if A is 0 or B is 0 or both A and B are 0. Yeah. So what you see is that you see a transistor network which looks like that. It looks parallel in the PMOS and it looks in series in the NMOS. Now let's do the flip version of this, which is A plus B. So why don't you guys try this and tell me how does the CMOS circuit look like?
Sir,
Yeah.
can you explain this upper part for
Okay. Let's recall the NAND gate. What does the NAND gate tell us? NAND gate output has to be high, right? Y is equal to AB under the bar, right? So guys, by the way, VDD is right there. This is VDD. The symbol for VDD is this. Symbol for ground is this. Okay. So what you let's go back to the question, right? We want Y as AB bar. That is, what is the truth table for AB bar? Truth table for AB bar is A, B, Y, right? Two input. So 0 0 0 1 1 0 1 1, right? So this is 1 1 1 0, right? So Y can go to 0 only when both these are high. For all other combinations, I need to pull Y to high voltage, right? Which means that I need to create short paths between Y and supply, VDD. So how do I do it? Supply should be shorted to Y if either A is 0 or B is 0 or if both of them are 0. So what I do is I connect a parallel fashion of PMOS circuits, right? Such that this PMOS transistor, if A is 0, this PMOS transistor turns on and it conducts current. And so basically Y gets pulled to VDD through this PMOS. Or if B is 0, this PMOS works and pulls Y to VDD. Or if both are 0, then both the transistors work in tandem to pull that node to VDD, right? So what's happening here is because this is a mostly one circuit, I see a parallel path because Y can go to VDD through transistors. Say let's call these M3, M4, and M1, M2, right? So M1 and M2 both have to have a high input at the gate to pull Y, but M3 and M4 either of them can help to short VDD to Y, right? So that's how you would design a NAND gate because NAND is a mostly one output. Right? And now if you look at the NOR gate, right? What is the truth table for the NOR? By the way, am I clear? Who asked the question? Sorry, I
yes,
didn't
sir.
recall. I
Yes,
didn't
sir.
see
Yes,
the name.
yes, sir.
Prajwal, am I clear?
Yes, sir. Yes, sir.
Yeah, okay, good. Now if you look at the NOR gate, right? Let's do the truth table for the NOR gate. So truth table for the NOR gate, again, let's look at all the input terms. So 0 0 OR is 0, so NOR is 1. This 1, so this goes 0. So what you see here in the NOR gate function is that it's a mostly 0 output, which means that I should have more paths for Y to go to 0. So what this will tell you basically is, again, what you've known from your NMOS design is that if this is your output Y, you know that I should have two parallel paths if I'm doing an NMOS only technology, right? So my Y can be pulled to 0 either if A is high or B is high, or if both of them are high, right? So this circuit will ensure that when even if A is high or if B is high, if both are high, Y will be pulled down to 0, right? So how do I get it pulled up to 1? I can get it pulled up to VDD only when the input combination is 0 0. So this will now transition into a series combination, and this is going to be a supply voltage VDD. So that's VDD, that's ground, right? So again, let's number these transistors. Let's call them the same: M1, M2, M3, M4, right? So what we know is for Y to go to 1, both M3 and M4 need to be shorted. And both M3 and M4 will be shorted when A and B are both 0. So there is only one condition which will short the path from VDD to Y. And that condition is given by A and B both being 0. Right? When either of them is a 1, then this condition fails. And so Y gets shorted to ground instead. Right? So what you see is generally, and this is what, so you see a dual between P and N here. right? That is when the NMOS is in series, the corresponding PMOSs go in parallel. When the PMOS are in series, the NMOS go parallel, right? So you see a dual happening. So generally, in design terms, we talk about anything connected below Y, we call this as a pull down network, right? So this is the transistor network that is pulling the output down. So it is giving a low. And this network is called the pull up network, right? So whenever you think about CMOS technology, you have to think about a pull up and a pull down network, right? And so always remember that the pull up and pull down networks are going to be duals of each other. That is, if one is in parallel, the other will go in series, right? So let's do the same condition. Let's do this now. Implement this in CMOS technology. Abhineet, for to understand that, you need to understand MOSFETs. Unfortunately, I don't have time to teach you that here, but you can't just flip a VDD and ground. MOSFETs, even though are used in one directional ways here, so it's not just flipping the location of VDD and ground. So again, remember, you have done this before. When I asked you to do the NMOS circuit, you have done the pull down network. So the pull down network in the CMOS and the NMOS only technology remains the same, right? So all you have to do is find what is the equivalent pull up network for this. Following me? Pull down network is the network which is pulling your Y to zero, right? Astha. What is pull down network? Pull down network is ensuring that Y goes to zero when these transistors get shorted. So the pull down network is going to get your output to zero. When the pull down network is enabled, then your Y goes to zero. When the pull up network is enabled, then your Y goes to VDD. Am I clear? Astha, am I clear? Are if you just grounded Y, then Y will become, if you grounded Y, how do you get a gate? If you ground Y, how do you get a gate? You want your Y to be a function of A and B, right? Am I clarifying your question? Do you want to come online and ask, unmute yourself and ask your question? I may not be following your question.
I just meant that isn't the pull-up network sufficient for Y, like without the pull-down?
No, it is not sufficient because if you suppose you didn't have the pull down network and you just made Y equal to ground, right? Then what's going to happen if there's no resistor here? Then Y is always going to be ground, na?
Right. Okay. Yeah.
Right. You need to also ensure it's not ground. When you're charging this Y to 1, you need to ensure that there's no connection between Y and ground. That's why these two become duals of each other. That is, Y will I. So remember, this is a good point. Always remember when you design the circuit, for any input combination, it should either have a it should either be shorted to VDD or it should be shorted to ground, because remember Y can have a value of only 0 or 1, right? So which means that either your input combination should short Y to VDD or your input combination should short Y to ground. If you've designed an circuit which has Y equal to being shorted to both VDD or ground at the same time, it's wrong. There's something wrong in your design. So always remember that at any point of time, only one of these networks should be shorted. Yep, that's that's exactly how you design. So again, remember, this goes as This was how you did A. So let me use the other convention for the gates. Right. So this was how you designed the pull down network. So this was your Y. So again, A is in parallel with B and C. So here A goes in series, right? So this becomes A, and then you have a parallel combination of B and C, right? And then you'll have supply voltage there. So remember, whatever becomes series converts to parallel between the duals. So I'm glad Arjun answered the question. So NMOS technology, Shiv, if you think about NMOS technology, you remember in NMOS technology, I showed this, right? There is this combination. This is nothing but a way you implement a resistor using MOSFETs. So what happens here is this transistor is always going to be on, which means that there's always going to be current flowing in the circuit, right? And so as Arjun pointed out, this is going to always leak current from supply voltage. So your ICC numbers are going to be very high. So if you want a design which consumes less power, you want to always ensure that only one of these networks are on at all times. So either you short VDD to Y or you short Y to ground. That way you reduce the power consumed in the circuit. Okay, and Mayank, you're right. Pull up is always PMOS, pull down is always NMOS. So always remember, will the pull up always be dual of pull down, Rahul? Don't try to catch me in my words. No, there are design questions where you can shorten this. We'll give you some training next week in the tutorial, right? So not necessary that pull up and pull down have to be duals, but generally that's the case. Pull up and pull down are duals, but you can come up with smart designs where you don't necessarily have to have duals. So what I want you guys to do now is, I'm going to give this question in the tute anyway because the rest of the class may not have it. But I want you to do the following. So implement a half adder and a full adder in CMOS. Okay. So go back, look at what the Boolean expressions for the half adder and full adder were, and try to see how do you connect them in a CMOS network. Okay. So once you get this field, then the rest of them should be pretty easy. So given any Boolean function, you should be able to draw the CMOS circuit for the same. Okay. So this is all I need you to know about CMOS in this class. So with that, we'll change gears to another type of a gate, which is known as a tri-state gate, right? So what's a tri-state gate? So if you think about a regular transistor gate, right? So a NAND, so a tri-state gate looks something like this. Suppose I take a 2-input tri-state gate. The gate has an enable signal on it. And then you have the output. Right? So if you look at a normal NAND gate, right? If you look at a normal NAND gate, Y is given by AB prime, right? That is whenever an input changes, Y will follow the input, right? And Y will follow it after some propagation delay. So if you think the NAND gate is 20 nanoseconds as a propagation delay, after 20 nanoseconds, if the input changes and Y has to change, then it'll take 20 nanoseconds for that propagation to happen. So at any point of time, Y can have a 0 or a 1 or a high or a low only, right? Y cannot have a third state. Y can only sit in two states, which is either a high voltage or a low voltage. Now what happens in tri-state is that you have the output can be either a high voltage or a low voltage or what is known as a high impedance. That is, it becomes an open circuit, right? So the output can have three states, which is high, low, and high impedance. And what does high impedance means? High impedance means that this output doesn't have a voltage level. It's an open circuit, right? And that is controlled by enable. So if you look at the truth table, of this circuit, when enable is low, you don't care what A and B are. This will be a high impedance output, right? And then only when enable is 1, you will get your standard NAND outputs, right? So 0, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, right? So enable, just like how we thought about enable for decoders, muxes, etc. This is an enable sitting at. So again, Mayank, don't worry about implementing this in CMOS. The implementation is not simple. So we are done with CMOS. Okay. Don't worry about implementing tri-state gates in CMOS. It's different. I'm just introducing the tri-state concept to you guys. That tri-state is a different kind of gate, which essentially gives you a third state at the output, which is a high impedance state. High impedance state basically means it's an open circuit. So it will not be able to supply you any current, right? Which means that there is no value. It's basically junk logic value. And similarly, if you look, and so you can think about the same gate as a active low enable. So I can think of, right? So this will tell me it's an active low enable or it's an enable, right? So you can define tri-state gates as either. Now, what is the advantage of tri-state gates? So tri-state gates become important whenever you're trying to share one data line over multiple inputs. Right? Suppose you have, so Gaurav, I'm going to talk to you. If you think about that, you have this one line, right, on which you have some data you have to send from this point to the other point, right? Now, suppose there are three inputs coming into A, right? An easy way to implement that would be, so you can also think of, there are what are known as tri-state inverters. So what I'll do is I'll just connect them in shorted out, right? So if you can ensure, right? So if you can ensure that at any point of time, only one of enable A, B, or C will be, if I can ensure that only one of them is going to be high at any point of time, right? If I design my circuit in that way, then basically that means that this only one of these gates will work, right? And when something is high impedance, so for example, if enable A is high and B and C are low, right? Then basically this becomes a high impedance output. This becomes a high impedance output, right? And so what's left is just A prime here, right? So and similarly, if my enable goes, B goes high and A and C go down, then B prime will come onto this bus, right? And this to remain high. So with high impedance states, it becomes very easy to implement an AND function. An AND function is just shorting all the inputs, right? So this saves you a gate. So many times people use this when you have to, and this is especially used when you're sharing bus lines. So in you'll see a lot of microprocessors and microprocessors when you want to share bus lines, you will use a tri-state gate, right? So a tri-state gate helps you with ANDing. When you want to AND signals, as long as you can ensure that one of the signals is high at any point of time, then you can use this to implement a single data line on which multiple data can float on, right? So let me ask you a quick question in preparation for quiz. Suppose I want only one of enable A, B, or C to be high at any given point of time. From which MSI should I take its output as? So I'll repeat the question. I want to ensure that only one of enable A, B, or C is high at any given point of time. So I can take the outputs out of one of the MSI components we have discussed in class. Which one would it be?
Decoder.
Decoder is correct, not mux, it's decoder, right? Remember, decoder takes in what? Decoder has n inputs and 2 power n outputs. right? So depending on the number that you input to the decoder, only one of the lines will go high, right? So it's the decoder that you'd use.
So
Okay.
for decoder, two lines can also go high if it's 0 1 1.
No, how can decoder lines go high with 0 1 1? If it's a two, if it's a 3 is to
Oh,
8
sorry, sir.
decoder.
Sorry, sir. Sorry, sir. Sorry.
Ha, ha, ha. Okay, so again, this is just a quick introduction to tri-state. Keep in mind that these options are available. Again, we won't use a lot in design. They'll be mostly used in like quiz questions and stuff like that. But design in this class, we'll stick to traditional gate design. So the last thing I want to talk to you about is what are known as CMOS transmission gates. So this is another transistor level design of doing CMOS gates. Right? So what we do in this case is a transmission gate, normally denoted by abbreviation TG, consists of of something which looks like this. Sorry. So it consists of a connection, basically I've connected an NMOS and a PMOS in parallel to each other. So how does the transmission gate work? The transmission gates works very simply is that the transmission gate is closed. That is X is equal to Y when N is equal to 1 and P is equal to 0. Right. So when I turn on the NMOS and turn on the PMOS, then my X is equal to Y. Right. And when so basically when N is equal to 0 and P is equal to 1, right? That is when both these transistors are off, then X and Y are open. Or I can treat my Y as an high impedance state. Again, let me repeat what a transmission gate is. A transmission gate is made up of an NMOS and PMOS in series between two nodes X and Y. Okay. X is equal to Y only when both these transistors are turned on, right? And the way you turn them on is you give a high voltage to N and you give a low voltage to P, then X is equal to Y. Else, Y is a high impedance. So one way to use that, for example, is I can design a circuit which looks like this. Let's draw a transmission gate. So I will just box it this way. So I can think of the transmission gate symbol as something like this. So it has two inputs, N and P, control rather, and X and Y, right? So for X to be equal to Y, N has to be 1, P has to be 0, right? Otherwise, Y is going to be high impedance. So if I want to design a circuit, so let's think about a circuit, right? Suppose this is my transmission gate, right? I can do something like this. So if I ask you to write the truth table for this circuit that I've drawn, what can you say? How would you write the truth table? Or how would you describe the circuit? So you'll say that when C is equal to 0, Y is high impedance, right? And when C is equal to 1, then X is equal to Y or Y is equal to X, right? And why is that? Because by connecting an inverter here, I can always ensure that whatever input is coming at this node, right? Suppose I call this node A, whatever is coming at A prime will show up at the other node, right? So by connecting this inverter, I can always assume that if C is 0, this will be 1. If this is 1, this will be 0, right? So typically this is how we think about a transmission gate, right? So Gaurav, let me take a few questions. So X is something we will be controlling. Yes, Sarthak, that will be the input. So we want to get Y as a function of X, right? So that's what we are doing. Gaurav asked, shouldn't any one of N and P? So you're right, Gaurav. Logically, either N or P should work. What happens with transistors is generally P conducts a zero better, N conducts a one better, right? And there, sorry, flip version, sorry. N conducts a zero better and P conducts a one better. And so therefore, when we use a combination of N and P because we want both 0 and 1 to be conducted. You can construct a transmission gate with only one of the transistors, but then what happens is that the voltage level at the output drops. So if you want to ensure that the voltage level of Y is the same as X, you use both NMOS and PMOS in parallel. Okay. Ramnathan, you're right. Right. If it's NP prime, then X is let through. Exactly. Otherwise, it's going to be a 0. Saksham, did I answer? I hope I answered why. Yeah. So Saksham, wait for ED. You'll get it once ED is completed. So in other cases, Ruturaj, the output is a high impedance. Okay, I'll show you how to use transmission gate. So let's do one example right there. I want to implement a function. I want to implement an XOR gate using transmission gates. So again, let's recall what the transmission gate looks like. A transmission gate is this. It's TG, X, Y, N, and P. So now think about how to implement an XOR gate. So we can think about it this way, right? I want Y to be B when A is, so you did this using a mux. Now we are using the similar logic for transmission gate. You want Y to be B when A is 0 and you want Y to be B prime when A is 1. Correct. Neil, you're right. Everybody following the logic? I want Y to be 0. Sorry, I want Y to be B when A is 0. At this time, this term drops off. And so Y becomes B. And Y becomes B prime when A is 1, right? So I have, so B, so my Y needs two transmission gates. One transmission gate will turn on when A is 0. One transmission gate will turn on when A is 1. So what I'll do is consider this circuit. Let's call two transmission gates. Right. So let's talk about the input B. So I want B to be sent to the output when A is 0, right? So when A is 0, what I'll do, I will, suppose this is my input A, I will take A, send it through an inverter to the N input and send it as is to a P, right? So this transmission gate TG1 will work when A is 0, right? Everybody following the logic? Why is that? Because when A is 0, N is 1 and P is 0, that is when this turns on, right? So this becomes B when A is 0. So what I've implemented here is prime B. Right? And similarly on this other side, what do I want to do? I want to pass a B prime, right? So let me create a B prime. And I want to pass B prime out to Y only when A is high, right? So how do I do the high connection? I connect A to N and I will connect A prime to, so I can pull this gate out, this output out and connect it to here, right? So TG2 will turn on when A is 1. So when A is 1, then I'm sending B prime. So this is AB prime. And the beauty of transmission gates is now normally if you've done it in a gate level, you would have put an OR gate here, right? But the advantage of the high impedance state is all I can do is just do this and Y. right? Because at one, whenever A is 0, this transmission gate is shut off. So there is no connection here. It's an open circuit. So Y just becomes A prime B. And when A is 1, this circuit turns off, right? And all you're left is just this circuit. So it's a very simple way of implementing. Now, if you think about this, how many gates do you need? How many transistors do you need? This transmission gate requires two transistors, each require two transistors. So you have only 6 transistors here to implement, right? 3 NMOS, not 6, sorry, 8 transistors. NMOS is 4 and PMOS is 4. Right. Now do the same, go back and try and see how do you implement an XOR gate using CMOS technology. So go back today, try and figure this out. And what you'll see is that the transmission gate implementation is a reduced number of transistor implementation. So in special cases, so again, you see that the transmission gate cannot be general. I mean, you can generally apply it to design, but it may not be advantageous. It becomes advantageous in certain special cases. For example, in this case, when you're doing an XOR gate, it becomes advantageous to design something this way. Okay. So with this, we will close combinatorial circuits. We will close digital logics. Digital logic families. So starting Wednesday, we'll start my favorite part of the course, which is sequential design. Okay. So now we'll introduce clock. We'll start now thinking how best to reuse hardware. Okay. Saksham, what I asked you is implement an XOR, 2-input XOR gate using CMOS technology and count how many transistors you need. And see if you can get the transistor count better than this or should it be worse than this. So Ram, by the way, I'm done. Those of you who have no questions can leave the lecture. Ramnathan, how do we intuitively describe the high impedance case state? Intuitively, it means Ramnathan. So if you think about when we discussed digital logic families, right? Whenever you see a 0 or a 1, it is associated with certain current flowing into or out of the gate, right? Whereas high impedance is something where there is no current flowing. The circuit is designed in such a way that the output cannot give or cannot supply or sink a current. So it is kind of a third stage where that output is hanging, if you will, right? So it's normally, I don't know intuitively how to think about it. It's not a 0 or a 1. It's a manifestation of the current and voltage at that particular node. Okay. How do we differentiate? Gaurav asks, how do we differentiate between high impedance and low as the output will be? No. Gaurav, I was trying to answer the same question to Ramnathan. 0 and high impedance are very different, right? When you say something is a 0, you know the voltage is a 0, there is some current coming out of that gate. Remember VIL, IIL and IOL, right? There are currents flowing through those gates. Now, when you have a high impedance, there is no current. So high impedance and low are not the same. That's why I taught you digital logic families. High impedance is very different from a low. In a low, current is flowing. In high impedance, there is no current flowing. Okay. Hariharan, how can you explain XOR again? All right, let's quickly do this. So are you comfortable with me calling the XOR gate this way? We know XOR is this. I can say that Y should be B when A is 0 and should be B prime when A is 1. Are you
Yes.
comfortable with me?
Yeah.
Okay. So which means that if A is 0, I need to send B to Y, and if A is 1, I need to send B prime to Y.
Yes.
Okay. Again, I'm trying to create intentional English sentences which will help you understand what the transmission gate is doing. So what I'm saying is that I want to send B to Y when A is 0, right? So what I'm doing is if I take TG1 for example, TG1, remember this is N and P. So for the TG to work, Y is equal to X when N is equal to 1 and P is equal to 0. Right? Now I want this TG1 to work when A is 0. Right? So for that, what I have to do, I have to take A and invert it to get a 1 at N. Right? That way I can turn this TG1 on. So TG1 will turn on only when A is 0. and at that point of time y will be equal to b because x is connected to b. Correct?
Yes.
Now if I look at tg2 on the other hand, I want tg2 to turn on when a is equal to 1, right? And at that point I will send b prime to y. So what I'm doing there is I am again giving my n input as a and p input as a prime, right? So this transition tg2 turns on when a is equal to 1, tg1 turns on when a is equal to 0. And so when tg1 turns on, my output becomes b. When tg2 turns on, my output becomes b prime, right? And now because when tg1 is turning on, tg2 is shut off, so this is an high impedance circuit, so I don't need to consider a gate. I can just short the two outputs. That gives me the functionality at the output. Am I
Yes.
clear?
Got it. Got it. Thank
Okay. So Sarthak, how did you get 8 transistors? So Sarthak, inverter requires 1p, 1n. TG1 requires 1p, 1n. So there are 4 components with 2 gates each. Na? So 8 transistors. Okay. So although TG is decreased the number of transistors in circuit, we still use CMOS because of um, yes, normally CMOS is used. We don't use resistors in TG, so CMOS is normally used, but sometimes for fast. So one advantage of transmission gate circuits is they tend to be fast. So when you have a speed critical path in your design, you tend to go to a transmission gate kind of circuit. As you said, obviously CMOS is going to be low power, so you won't use TG all across. But for speed sensitive circuits, I will use TG. See, these are all choices that a designer has to make, right? You have to deliver a design. How you deliver design, you have to make the right choices. Okay, Nishant, how do you differentiate between no power supply going into the chip and high impedance? See, you have to come to the lab for this. What is no current, right? You talk when so let me ask you in ES. You guys have done ES. What does impedance mean? How do you measure impedance? Nishant, how do you measure impedance?
Sir, I don't remember impedance.
Okay, think about any of your high school 12th physics lab. How do you measure resistance?
V upon I.
V upon I. So if I want to measure resistance, I apply a V and I get an I, right? Now in the case of a power supply, right, if I shut down the power supply, right, my current is going to be 0, right? If I measure the current, I'll get a 0, right? Because my input voltage is a 0. Whereas in the high impedance case, no matter what voltage I apply to that node, it is always going to give a current of 0. So it's kind of an open circuit. Do you understand the difference between the two?
So in one case there'll be voltage, and if it's off, then there'll be no voltage also. Is that right?
Yeah. Hello. Am I audible?
Yes, sir.
Okay, sorry, my computer got disconnected. So Sanika, uh, can you can you explain to me why you think it should be a mux? Maybe we'll start there.